My name is Bodner. I'm an assistant professor at University of Technology. I'm very happy to be here on the invitation of the Austrian Cultural Forum here in Warschawie. And I've been invited to give a bit of an introduction into what we are working on in terms of hydrogen technologies, what is the status of our research, not just us in Graz, but altogether of the, let's say, industry and research behind. And what is the outlook, where are the challenges that we see and we think that we need to address with our research. Not sure how much this is needed, I guess very much. I will start a bit with an introduction of Graz University of Technology, where I'm from, that you also have a picture of who's in front of you today. Then I will talk about the global energy and hydrogen demand, because I think there's a lot that needs to be put also in perspective when we're talking about new technologies. And then, as promised, I will be talking about the challenges of these technologies and where we see the biggest need for research. And since it's a very small audience, I'm happy to be interrupted and have an active discussion in case there's anything that you would like me to delve into more details. Okay, so in case you don't know where Graz is located, we are in Austria in the southeast. This is where we are, and here's some impressions of the city, of the main square, of the Museum of Modern Arts, and I think the most important landmark, the Turm, which is defining, let's say, the picture of the city. Graz is the second largest city after Vienna in Austria. We have roughly 300,000 inhabitants. And if you want to get a picture of the city, I think the next number is actually a decisive one, and that is that of these 300,000 people, roughly 60,000 are actually students, because we are really a student city, and Graz University of Technology is the second largest of the 6 universities that we have in the city. Some impressions of the university. A lot of the appeal is that it's actually a bit spread out throughout the city. So you're not just on one big campus, but you have the feeling of actually being part of the city, working or studying at the university. And some numbers, which I don't want to bore you with too much, but I think it's also important to note that actually the university, first of all, of course, the students are very decisive for the city itself, but also it's actually quite a significant employer for the people of Graz as well. Graz University of Technology, we're organized in 7 faculties. I don't want to bore you with that. Where I'm from is the Faculty of Technical Chemistry, Chemical and Process Engineering, and Biotechnology. In that faculty, we are the Institute of Chemical Engineering and Environmental Technologies. Now you might or might not wonder why hydrogen research is located at this institute specifically, because in the end, hydrogen technologies are very interdisciplinary. And actually it has more of a historic reason, and that is because our research dates back to Prof, who has been a pioneer in the research of especially alkaline fuel cells, but I would say hydrogen technologies altogether. And you can also see why he has been quite leaving an impression on the, let's say, technology. He started off building his own motorbike, as you can see, based on hydrazine, which is, for the non-chemists, maybe not so easy to picture, but actually it's quite a dangerous substance. But the story goes back then, it was not causing cancer yet, because they simply did not know. And then he also built his own car. Basically, he refurbished a car to drive also with fuel cells. And maybe a nice little anecdote to that as well. Apparently, he did get only one prize for that car that he built, and that was not for the engineering behind, but actually a design prize because of the red gas cylinders on the roof of the car. So a little bit of a story of the background also, where the research has started and that has stayed with the university and with the institute in particular. So this is kind of like the roots of it. But let's talk about energy, and let's talk about hydrogen. And as I said, I think it's very important to look at the global scale in order to actually understand where hydrogen comes into the picture and why it's relevant. And here I have brought you a graph of the energy, the global energy demand and supply from 2 years ago, 2022. This increases only or fluctuates to an extent, but mostly these numbers still stand, and we use roughly 180 petawatt hours a year. And this is now not something, not a unit that we are typically hearing of. So this is 10 to the power of 15 watt hours of energy. This is a lot of energy. And as you can see, and I think also have an idea of, the majority of this energy stems from fossil fuels. So 76% roughly stem from fossil fuels. Roughly 4% come from nuclear energy, which is neither renewable nor fossil by the definition. And 20% are renewable energy. And now, when we talk about hydrogen, I think it's important to be aware of one fact, and that is that already today, 2% of this energy globally are used to produce hydrogen, actually. And this is a lot. And also, this is not a coincidence that it's located very much in the black part, not necessarily because it's all from oil, but it is all pretty much based on fossil fuels. Let's have a bit of a closer look into the hydrogen we're talking about here. So these 2% also represent 80 megatons of hydrogen per year that are being used. I already said more than 95% of it originating from fossil fuels, and only a very small amount is actually used energetically. So the biggest shares are used in refining and are used in the production of ammonia. So we use it not as the compound as an energy carrier, but we use it as a chemical compound in these processes. And a little bit indicated in green is basically all the rest, which includes the use for example, electricity. So the energy use. And you can also see that it's increasing a bit, but it really plummeted in 2021. And I think that is quite harsh truth also that we have to face with hydrogen. That is because all of the demonstration projects, the ones that would be basically done only to showcase how hydrogen can be used energetically, were discontinued or put on pause during because of COVID. So there's a lot of this also basically only driving towards showing and demonstrating that hydrogen is feasible as of today in the energetic use of it. Let's have a bit of a look also at predictions. Without a laser pointer here on the screen, it's a bit difficult to show, but we estimate an increase here based on just how we expect industries to grow. But also there's a lot pledged, and a lot pledged in particular for the energetic use of hydrogen now. So you see that the green bar until 2030 increases. But at the same time, also an undesirable truth about that is that actually this would be how much hydrogen we would use altogether now, not anymore differentiated by different applications, in order to meet net zero emission targets by 2030. So we are talking about a significant increase in the usage of hydrogen, but if we want to reduce emissions to the extent that we intend and hopefully achieve, we have to do much more. Also, I think an important number if we look at mobility and the energy that is needed for mobility and transportation, this is roughly 30% of our global energy demand as of today. And if we would switch over entirely to hydrogen, we would need approximately 1,700 megatons of hydrogen per year as compared to the 90 that we're using right now. So a lot of need if we want to switch over entirely to increase capacities. But, and this is now a positive aspect, there's a lot of willingness to move, and there's a lot of willingness to invest. And here you can see some of the country situations of where hydrogen is either already being produced specifically for the use in mobility, or where it is planned and putting into realization. So you have the dark green bars that is already in operation, hydrogen for mobility, and you have the lighter green bars that show how this is already planned or already in construction. But, as I said, we have to face the fact that hydrogen as of today, the majority is not green hydrogen, is not renewable hydrogen. And for that, I think it's also, again, important to look into where our hydrogen comes from as a matter of fact. And if we look at it, we can see that the hydrogen we are producing today is significantly emitting CO2. So we are here emitting roughly 830 megatons CO2 per year for the production of hydrogen that is going then to be used as a chemical compound. And this is more than the whole country of Germany is emitting, and that is also more than global shipping is emitting. So it's very important to switch over where our hydrogen comes from while we grow the hydrogen industry. And I think you are probably all familiar with the term green hydrogen. Hydrogen has colors assigned depending on where it originates from. So let's have a bit of a closer look at them. Hydrogen originating from coal or lignite, for example, is called brown hydrogen. And you can see here also on the right-hand side how much is being emitted in kilograms CO2 per kilogram of hydrogen being produced. So you see this is the biggest share. If we are having hydrogen from natural gas, it's called gray hydrogen. There's more colors than are listed here. These are just some of the most prominent ones. Then it already goes down a bit. There's also the approach to have hydrogen from fossil fuels, but using then CO2 capturing techniques in order to prevent the actual release to the atmosphere, bind it, and ideally also put it into use again, ideally have it in some kind of circle. But also we can have green hydrogen, which is from renewable sources. For example, from biomass or biogas. Still we do have some emissions, but far less. But what we are working on and what we are most interested in is electrolysis. Because there we use electricity, we use, for example, electricity from renewable energy sources, and we convert water with this electricity into hydrogen and make that completely CO2 independent or carbon independent. Why would we want to go this route? Well, it's sustainable. It's the only pathway to hydrogen that is entirely carbon-free, where we are independent of carbon sources. It's versatile in the end, as I've already shown you. It is already a big, large-scale used chemical compound. If we want to add to that the use for energy or for propulsion, we will have to scale up, and we'll have to make sure that that is also CO2-free. And of course, it allows us to store energy. Renewable energy sources fluctuate, we all know that. The sun doesn't always shine, the wind doesn't always blow, and also tidal energy is not always consistent. So all of these different renewable energy sources fluctuate throughout the day, throughout the year, throughout the seasons, essentially, and we want to be able to store that energy, take it, for example, from summer to winter and use it when we actually need the energy, and multi-stabilize our energy grid with that. So there's a lot of motivation why we want to go towards using hydrogen at scale, produce it as well as store. Yeah, I think this one I will skip. This is basically a repetition. So we see that there's a lot pledged, that there's a lot of growth in now the production capacity of electrolyzers. So the idea is to increase the capacity of producing electrolyzers themselves. But also if we're looking at what has already been pledged, here, this doesn't work, in light green still we see appreciate that if we want to meet our targets, if we want to have the type of society and infrastructure that we need to reach the net zero emission targets for 2030, we have to do even more than is now being pledged and planned. Yes? Okay, good. So let's have a bit of a closer look at the technologies themselves that I'm talking about. This was now big numbers about the energy supply. Let's look into the details of the technology. And there's two technologies that I'm personally working with and my team that we're researching on, and I will show both of them essentially to an extent because they face fairly similar challenges. And that is electrolysis as well as fuel cells, both hydrogen technologies, electrochemical conversion of energy and hydrogen in different directions. When we're looking at electrolysis, basically what we do is we use energy to split water. So what we need is to apply a force to put more energy in as we drive the reactions. The higher my current, the more hydrogen I'm producing, the more energy I will need. And any kind of loss, any kind of resistance will increase the amount of energy that I will have to put into my system in order to have the reaction going. This is, of course, water electrolysis, which we will be focusing on further on. But this is also, for example, electroplating, metal reduction. There's several different types of electrolysis. When we say electrolysis, we mostly think of water, but there's a lot of technologies actually behind the term electrolysis. And then there's fuel cells, which are the opposite. There, I'm putting in hydrogen and oxygen or air, and then I'm using the energy that is in these two compounds in order to generate electricity. So there, the more energy I'm consuming, the more reactants I'm consuming, the lower my voltage, which means that I cannot infinitely convert, that I cannot have, it's not a perpetuum mobile, it's a finite source of energy. And this is fuel cells, but this is also, for example, a battery. So these are called galvanic cells. We are using the energy of those, and there's multiple examples. We talk about fuel cells today. Let's have a look at the principles. Now in the, let's say, the chemistry of it, or the electrochemistry of it. On the right-hand side, you have the fuel cell reaction. We supply hydrogen and we supply an oxidant, we supply air. And through the electrochemical reaction of them, so we have separate reactions happening on an anode and on a cathode. And as these reactions occur, I have energy that I can use, that I can consume externally. And an electrolyzer cell is basically everything in reverse. I'm pushing in the energy, I'm splitting water, and with that I'm generating oxygen and I'm generating the hydrogen. I hope this is so far not confusing too much. And in the end, we have electrochemical cells in both cases. They are a bit different, but altogether they are fairly similar in their composition and fairly similar also with the materials that we use. And this is what I want to go into a bit more detail now, in order for then also you to understand where the challenges are when we're talking about these technologies. So again, fuel cell mode, we put in hydrogen, we have water being generated, we put in hydrogen and oxygen, we have water being generated, or in electrolysis, we put in water with hydrogen and oxygen being produced. The shared compounds now, you can see here, some of these are abbreviated, but I will explain them a bit more in detail. So we have a polymer electrolyte membrane, which is an electrolyte, an ion conductor that I need for my electrochemical reaction. I have a catalyst, an electrocatalyst. This is platinum, which is a very costly compound. And we have carbon-based structures, because basically we have a reaction between a liquid phase and gas phases. So you can imagine that you have a lot of movement of these compounds to the reaction site and away from them. So there, the structure and the transport properties are very, very important for us. And it's mostly carbon, which is, I think, a abundant elements to the picture. Yes, and then the electrolysis is a bit more of a challenging technology than the fuel cell is in terms of materials. So we don't get away with using carbon and platinum as much as we do in fuel cells. So there we have a harsher environment, meaning that we cannot use carbon. Instead, we need to use metals such as titanium, which is more noble and won't be chemically degraded by the environment of the electrolyzer, namely the oxygen. And we use instead of platinum also iridium as a catalyst, which is even more scarce. And for these technologies, there is a status that we understand fairly well, where we say this is our technology at the moment, but of course also for an industry and for us as researchers, we need to define targets. So what I want to show you now is also where the technology should go eventually, because we all need targets. Lifetime for now a fuel cell depends on how we use it. There's lots of different types of application in which we can put a fuel cell. As an indication here for heavy-duty application would be that we are around 16,000 hours of durability of the fuel cell, which is already quite nice actually. Obviously there is no ultimate target. We always want to have a longer durable material, but at least as a target for 2030, it's set with 28 or let's say 30,000 hours of durability in this particular application. System output is just a matter of scaling. Basically, this is around 250 kilowatts per unit. Efficiency, again, depends very strongly on how we use it. In stationary application, we can use heat. We don't care so much about the electrical efficiency. We are okay with lower efficiencies, something like 30%. If, of course, we want to go into transportation, we don't care about heat. We have no use for heat in a car, unless we need to heat in winter, but that's not going to be up to the temperature fuel cell is operating at. So we want to have as much of our chemical energy converted into electrical energy as possible. So there we're talking about around 60% electrical efficiency for transportation. Costs, I think there's also similar as to lifetime. There's no, it's too cheap for these types of technologies. As, let's say, a bit of a feeling for the technology, we're talking about 100 euros per kilowatt at the moment, should go down to 40. And operating temperature, I already said, if we can use it stationary, it's nice, and we can use also thermal energy, and we can use the heat that the fuel cell generates. But if we want to implement a fuel cell, for example in a car, we need to also think about how to get rid of the heat. Fuel cells, low temperature fuel cells that we are working with operate beneath the boiling point of water, which is 100 degrees C. But this is also very limiting if you want to reject heat. Heat rejection also depends on the difference in between your temperature and the ambient temperature. So you want to have this difference as big as possible in order to efficiently get rid of it. With 100 degrees C, we are not that far from ambient, typically, especially in summer if you drive on the road, that asphalt can easily also have 60 degrees C. So we don't have that much of a difference. We are having a hard time with rejecting that heat. So there's a lot of interest in going to higher temperatures there as well, which is, though, of course, very, very challenging for our materials. And I will show you a bit more about that. Electrolyzers, we also have, of course, targets. Their durabilities are much longer. We are roughly at 40,000 for this type of technology. There are several types of electrolyzers, as I already mentioned. Target, again, as much as possible, but at least for the foreseeable future, here 2026, 80,000 hours of durability. Efficiency in electrolyzers is a bit higher, so between 65 and let's say 70% is fairly reasonable. Costs, higher again for electrolyzers as compared to fuel cells, roughly $1,000 in this case, because this data is from the Department of Energy in the US per kilowatt. But in the end, what actually matters the most, of course, for a consumer, for an industry, for us as a society, is the cost of the hydrogen in the end. And there we are above $3 per kilogram of hydrogen, with the ultimate target being $1. So this is the $1 target of the US at the moment, the hydrogen shot, as they call it. And performance, then, I think this is basically just a result of everything of the rest of the efficiency, but some numbers that you have a feeling for those interested. And important there also, PGM, platinum group metal usage. I already talked about platinum, I already talked about iridium. These are two scarce materials. So let's have a bit of a closer look at the scarcity of these materials, of these metals. And you might wonder what the blue bar in the bottom is. And if you pay attention, you might also wonder what these two stripes are right there, if you can even see them. No? They are here. This is the concentration of the big blue bar in the bottom, nickel, in comparison to the concentration of platinum and iridium in the soil, so that you get a picture of the scarcity of these two compounds. So they are both extremely scarce in comparison to a relatively cheap material, but still nickel is not that cheap actually. So just to get a bit of an impression about what we're actually talking about when we're talking about these metals. And also, if we look at how much we would then use or need, if we want to increase the capacity of electrolyzers according to the targets, essentially. Talked a lot already about how we want to scale up hydrogen technologies. If we would use state-of-the-art 2020 materials, we would need roughly 675 tons of platinum, iridium in order to realize this. This is a lot. If we would be able to reach the targets, and we are on course of that, for 2030, it's a tenth of that. That is substantially less already. And if we then look at what is being produced annually of these metals, which is of course a bit of a tricky thing because it's not necessarily linked purely on availability, it's also very strongly depending of course on demand. So it's not an easy number actually to use, but still just to have a bit of a feeling for the numbers around. Annually, 2022, roughly 211 tons per year of platinum, and roughly 8 tons per year of iridium. So you can see, and I hope this is a not too bleak takeaway, but you can see that we are talking about substantial amounts of these materials that we are going to need. But if we reach the targets that we have set for the materials, it will add up, it will work out. Not easy, but it does work out if we look at the numbers. But for sure it's a challenge that we need to address. Another challenge upcoming, and I'm not sure, but I suppose that this is also something that you might have already heard, is a pending ban on perfluorinated substances, alkyl substances. Where there's a lot of question marks, so I've intentionally phrased them as questions. What is actually included? What are these PFAS? Because they're everywhere. They're in almost everything, in clothing, in cars, in fire extinguishers. Which substances will be included? How far will it reach? When will it also come into action? For which substance? Will there be exceptions? For how long? And what will it bring for the future? These are questions that nobody is really able to answer right now. So there's a lot of question marks, and you can also see here an example of them, and I don't want you to learn the structures by heart, but I can promise you will see them again. These are examples for these types of substances, but it's a whole lot. It's really a lot of different substances that are affected by this, and also they are in fuel cells and electrolyzers. Because we have already mentioned there's a polymer electrolyte membrane. That electrolyte is also called ionomer, and this is what it looks like. And if you remember just 2 slides ago, this is exactly the same kind of structure that we're talking about. I already said these substances are in many different applications, are in many different materials hidden, but they're also one of the core functional materials of fuel cells and electrolyzers. So this is something that has outstanding properties, these materials. They are very stable, they are very durable, they are very handleable. We have really worked a lot in research and industry, of course, as well, in stabilizing them and making them as functional as possible, as stable, as durable as possible, and fitting them to our needs. It's a hard one to replace. What we're working on also in my group at the Institute also is the detection of this. Because another question mark in this is not only which compounds do we actually need to replace, but also what is actually emitted. What do we actually get out? And this is very tricky to measure, not just for fuel cells, but for us, of course, as well, because we want to have a fully sustainable technology. We don't want to just cause the next problem with this, right? So one of the things, of course, that we're looking into is what comes out of the fuel cell, how does it degrade, what are the products, and also in the end it gives us a good indication on something going wrong in a fuel cell, because nothing should come out. What you see here is a method that we have developed for the detection of fluoride ions being emitted, where through the change of color of a reagent we can identify issues in the cell. A little bit also on what should be or what the intended developments for now these membranes are. There's a lot of detailed development still and optimizing them and tweaking them, but in the end the bigger goal is to move towards different technologies actually, to move away from the perfluorinated substances. As I already said, very difficult to replace, but there are things that can be done and that are being worked on, some also on the verge of commercialization. There's a big interest in also changing to alkaline environment, alkaline ion exchange membranes. There's also an interest in going to different types of structures, and I think pictures say more than all of the words, where basically we replace this Teflon type structure with aromatic structures with different polymers altogether. But of course, if we change something that fundamental, we change everything else with it. So this is quite a challenge ahead. And also a lot of the things that we have developed already for the materials and for the technologies as they are, we will have to rethink. As an example, fluoride ion detection has helped us to monitor the state of health. If we take away the fluoride, that's great, but also we're taking away our means to quantify degradation. So we will have to rethink also in how we can monitor how well these materials behave. Catalysts, already mentioned, they're scarce. We do want to reduce them as much as possible. State of the art, we're really focusing still, or when you go and if you go to a company and you want to buy an electrolyzer or a fuel cell, you're most likely going to get one with platinum and the electrolyzer with iridium in it. These are also processed. This is processed at scale. This is in place. But there's of course many motivations to move away or to improve there. So we want to, of course, reduce cost. We want to mitigate the whole question of scarcity, or at least as much as possible. And of course, we also want to increase durability, and we have to also have good processes in place. There are processes right now to produce these materials, but there's a lot still in the growth, basically, because these are emerging technologies. Where is the interest and the focus? Lower loadings, so reducing the amount amount, either just by having less, literally, and have that work, or by adding different metals to basically dilute our catalysts, or to switch over to something entirely new, which of course is a huge challenge. And here you can also see some, again, more to give you a feeling about the maturity of these alternatives. You see here on the right the colors indicating the technological maturity of these technologies. So platinum, no problem. If you want to buy a platinum catalyst for a fuel cell, you can go online and buy one and get it, maybe not tomorrow, but at least in a very reasonable time, very reliable. If you want to have something a bit more exotic, or where you have already less platinum on it, for example alloys, they are there, you can buy them, but it's maybe not so easy anymore, and maybe not so reliable as well. Maybe there's one supplier only, but they are out there. If you want to have more complex structures, it's all with the idea to reduce the amount that you need for the same functionality, so you can have all kinds of structures, essentially, of these. Then you start to get a bit more of a challenge. So core shell, for example, is one. You still might be able to get some samples rather from a research laboratory in that case than a company, but it's out there. But there's also ideas like nanoframes and shape-controlled crystals. That is really research work, and you might have to go to the laboratory and synthesize it yourself. So right now, there's not really an easy next candidate, essentially, in replacing the platinum, the classical platinum catalyst, as we have it, maybe the alloys, but that's about it. So there's a lot still to do. And one other thing that I think we should also bear in mind, and is often left out in the discussion, is actually recycling. Because if we look at it, in fact, platinum recycling works quite well. It has a very high yield, meaning that we get a lot of the platinum that we put into the recycling process also out as pure platinum then. And of course, it's also important to look at the footprint. If we want to have any other material, any other metal, we still need to mine it maybe. For platinum, and I'm sorry this is in German, but you see here on the right concentration of platinum in your respective sample. In orange, the ore, so the ore that you have to mine from the soil, from the mine, has very little platinum actually in it, even if you're already in a platinum-rich mine. So this is very low. You need a lot of soil moved for very little platinum. You have then computer parts, phones. There's some platinum in those as well. But if you look then, for example, the gray bar, the big one, is car catalysts, actually. Not of fuel cell cars, but of your regular internal combustion engine car. There's a lot of platinum group metals in there already. And of course, if we incorporate then the fuel cell stack into our recycling process, it's really concentrated there. So there's a lot of potential to have fuel cell technologies and also electrolyzers, of course, implemented in a recycling process. So we should not only look in terms of from a mine to my fuel cell car, but also what can I do with that later on. And then I'm moving to the next material, which is a little bit, let's say, overlooked sometimes, because we think gas diffusion layers, storage transport layers. I already said carbon-based materials. What about that? I mean, it's just carbon. Who cares? Actually, there's a lot of reason also to look into that material as well. That you have had a look. Basically, you have a carbon structure. It's responsible for bringing the gases to your reactive site or the water if you're looking at electrolysis. And then you also have to, of course, soil moved for very little platinum. You have then computer parts, phones. There's some platinum in those as well. But if you look then, for example, the gray bar, the big one, is car catalysts, actually. Not of fuel cell cars, but of your regular internal combustion engine car. There's a lot of platinum group metals in there already. And of course, if we incorporate then a fuel cell stack into our recycling process, it's really concentrated there. So there's a lot of potential to have fuel cell technologies and also electrolyzers, of course, implemented in a recycling process. So we should not only look in terms of from a mine to my fuel cell car, but also what can I do with that later on. And then I'm moving to the next material, which is a little bit, let's say, overlooked sometimes because we think gas diffusion layers, storage transport layers, I already said carbon-based materials. What about that? I mean, it's just carbon, who cares? Actually, there's a lot of reason also to look into that material as well. That you have had a look, basically you have a carbon structure, is responsible for bringing the gases to your reactive site or the water if you're looking at electrolysis. And then you also have to, of course, remove the products. So it's very important in how the porosity is, how the shape is. It also conducts electricity, and it modulates the water amount that you have directly where your reaction happens. So it's a very important layer for the functionality of both technologies. And it also has one important additive. There's a lot more to it that I won't delve into the details now, but it has actually PTFE, Teflon, perfluorinated substances, as an agent that is added to it in order to optimize the properties. So also there, we again find compounds that we are not too happy with. For electrolysis, it's a bit more challenging. I already said there's also the need to add metals, but again, this too has to be very fine-tuned in terms of the properties. I won't go into every detail there. But basically there also we have a lot of interest in developing, in moving away, in improving the materials and making them actually fundamentally renewable and environmentally friendly and sustainable. So a lot that can be improved, and I think I will not go into every detail. Structurally, treatment-wise, what we have done is what we have developed is a alternative coating where with a conductive polymer we can replace the PTFE, protect the fiber, make it more durable, and also modulate the water management better. And that leads me to the last question in this presentation before I conclude. And that is, all of that is nice, like there's a lot of challenges in the materials, but actually, like, what about now application? Because in the end, nice if there's an alternative coding, nice if there's an alternative approach, but in the end, what are the actual challenges if we put this into application? Of course, this is also something where we have looked into. And we know that actually when we look in the laboratory at the durability of materials, we benchmark and we look into some of the critical aspects during application, but we might not look at the full spectrum because this is very specific, the question. And if we replace a catalyst, we will not look into the whole bulk of possibilities of what can go wrong if only anything related to the catalyst is actually critical for us. So what you see on the right is basically the whole picture of what can go wrong, now in this case in an electrolyzer. So what we're also working on is to develop stress tests. Now, more for the application side. The question there is really, when I operate, if I put now, for example, my electrolyzer and couple it directly with, in this case, the real profile of a photovoltaic module. If I would take my electrolyzer, connect it to a PV panel and see what happens, how does it fare? How does it cope with that? How does it cope with the dynamics? And you see there, again on the right-hand side, the pattern of power supply to my electrolyzer of this module. And you can see You have some dips, you have some fluctuations. It's not as dynamic as you might think at first when you're thinking of a cloud passing over, blocking the sun. It's not that dynamic actually, but still dynamic enough. And one of the big challenges is there then actually the shutdown. So how do you cope with it at night? How do you actually operate your electrolyzer when there's absolutely nothing? So this is something that we have been able to show with our research, that it's not so much the dynamics that impact the electrolyzer, but rather the way that you cope with there not being any sun at all, so at night. Another thing that we have looked into was the effect of contaminants. Electrolyzers need water, and they're actually also quite often criticized for their consumption of water depending on where we want to put them. So of course there's a big interest in actually either using seawater directly, which is very tricky to do, or to purify seawater as simple as possible. So a study that we have done was to mimic the amount of chloride ions, so from regular salt that is in seawater, that is still left over after common water treatments of osmosis. So you get roughly 10 ppm of chlorine remaining in the water that you can fairly easily get from seawater. You can, of course, purify a lot more, but this is kind of like the easy approach, let's say. And we implemented that into an electrolyzer, and now you don't need to be experts in scanning electron microscopy, because I think it's quite clear at the bottom. You have the reference with ultra pure water, everything fine on the top, and I hope you can see it well. You see this yellow surface on the left of the picture, and peeking through are some red spots. So basically we saw that the catalyst layer in this part deteriorated by the presence of only 10 ppm of chloride over 50 hours. So this is next to nothing. So we have to be very, very careful with how we operate our electrolyzers, and we can do a lot of work on optimizing the components when there's still such critical intrinsic issues in it. To summarize, hydrogen is already a widely used compound. It's already there. We don't have to talk about maybe hydrogen will come up as a compound itself is being used at scale. If we want to talk about growth, if we want to use it for other means as well, if we want to use it energetically, of course we will need to look into a lot, but it's already there and we know how to cope with it for the most part. And it can, because of that, be a key facilitator to move to renewable and sustainable energy supply. But it's very important still that we reach the targets that we have set for the materials and for the technologies in order to make this possible at scale. And some of the goals we can achieve by engineering, by optimizing, by tweaking here and there, but some of these targets we can only achieve if we really go into the details of the materials and develop on the material level. Membranes to move away from potentially harmful compounds like perfluorinated alkyl substances. Catalysts to ease the strain on supply chains. And, of course, also all the other layers that we might easily overlook because we are just focusing on the most costly parts, but there's much that we have to improve in other layers as well. And of course, when we move away and if we change one thing, we have to be aware that it impacts a lot about the technologies, their behavior, the way that they age, and also their sensitivities to, for example, contaminants. So we have to have the development and the change in the materials move along with the research into how these materials age. And with that, I want to conclude. Thank, of course, my team and people at the Institute, funding naturally you for your kind attention. I hope it was interesting. I hope it was not too much chemistry. And with that, I would like to close. Thank you very much. And I'm very much hoping that there are questions and there's the discussion.
Not most of the questions will come from my side, but I do have two questions. The first question is basically the round trip efficiency. And if you see any application for hydrogen for the energy storage at all, because if we assume that we are producing hydrogen somewhere offshore, we have to desalinate water. AC/DC conversion is also not 100% efficient like any of the technologies. Then let's say PEM electrolysis 65–70% efficient. So in the end, we'll get 30–40% of losses. And then if we convert that hydrogen into electricity again, maybe we'll get the efficiency of. The losses will be even more higher. So do you think that there's any application for hydrogen for energy storage at all, or we should basically focus on using hydrogen where hydrogen has already been used, like oil refining, ammonia production? I don't know. Basically, all those applications where hydrogen is already in place.
These are two different questions, right? This is for the one part, the possibility to use hydrogen for the renewable energies, and I think there, naturally, efficiency is always important. We should not overlook that. But the technologies we're working with, we're very used to having low efficiencies with our internal combustion engines as well, where we're just getting out of fossil fuel. I don't want to think about the efficiency of having had this fossil fuel being produced throughout history, right? I mean, this is an unfair comparison. If we're looking at something that we take from nature that has been produced over hundreds of thousands of years, as compared to a technology that tries to capture the energy that we get from sun, from wind. So this is a difficult comparison in terms of efficiencies. If we have an abundance of electricity, also we will want to store it regardless. What are the alternatives? It's not really possible or feasible to have the scale of energy that we're talking about here stored in batteries. And then what else do you want to do with an excess of energy from wind or from solar? I don't want to say that efficiency is not the most important part here, but it is just one factor still in the whole set of things that we need to take into consideration if we want to look into storage. What else do you have? It's a question about the alternatives here as well for the storage of renewables. And the second part, sorry.
So basically the industry is the off-takers of hydrogen. Should that be energy storage, or should we just focus on hydrogen production for the sake of supplying that clean hydrogen to the industry that have already been using it?
Yeah, I mean, I think that for sure this is an important aspect also in the scale-up, because we have to activate the consumers of hydrogen that we have already, because you have, with the growth of the industry, you don't want to put an electrolyzer into place, produce the hydrogen and have nobody using it because there's no systems in place. I mean, that would be the worst case, and that's going to have the technology fail dramatically if we don't make sure that we match the production and the need already. And there it makes, of course, a lot of sense to first move over the industries that are already using hydrogen before we want to also grow then the need for the energy. This is something that should go hand in hand, and if we don't manage that, then we will have, of course, an issue with having that technology being viable. Yeah.
Es ist Möglichkeiten, wenn du schickst diese Präsentation für uns, aber wenn ich schicke E-Mail zu dir, kannst du schicken diese Präsentation für uns? Ja, das geht.
Aber es wird auch online gestellt.
Ah ja, okay.
Also
Und okay, sorry, English. The question is from the business side. Where is the money on this side? Because, no, this is no joke. This is no joke. Because only 45 cars we have on the hydrogen here in Warsaw. Only in Warsaw, not all Poland. I saw the Toyota sales presentation. But where is the money for the future for me and for my company? I'm from the investor side.
I mean, that depends on which side you're interested in on it, right?
But everyone says it's good money, but where?
Yeah, I mean, I think quite honestly, right now, the most reliable money is if you make testing equipment for fuel cells.
That's right.
And electrolyzers.
That's right.
There is a lot of money to be made right now. If you produce for research and for companies testing, you're on the safe side. There's money to be made today.
For next, you know,
for next,
your research is from.
Yeah.
I check your science way. You are from on this side from 2011, so you know, long time.
Yes.
Show me the case. Where is the money? I will give you, no problem. But you know, everybody say Japanese, Chinese make money for this, you know, and you know the capital from United States don't know, Israeli also, but I know this is a huge opportunity for this. I know some Japanese in Poland they make hydrogen.
Yeah.
I think so. There's a good way for a business.
Yeah. In the end, as also said before, if you sell the hydrogen,
That's right.
then you have the first step, and then of course your customers are the question. But if you can sell hydrogen to industry that uses the hydrogen anyway, you can bet easier on the rest growing. I would not right now myself.
Yeah. It's,
You know,
point to your science point of view. You know.
No. But I mean, my point is that electrolyzers, there's a huge need for that, and also a lot of the numbers and the comparisons are changing rapidly because the price for gas changes, the price for oil changes, the price for
energy.
Sorry?
Energy market.
The energy market is completely moved, it's been toppled over entirely. So a lot of the assessments that have been made in terms of economical viability of electrolyzers are looking very different right now. And especially if there's a growth in renewable energy, there's a market to take up also the excess energy.
That's right.
If we have all of Europe producing photovoltaic electricity at the same time, our grids will not handle that.
That's right.
So there is money to be made in electrolysis. But of course, it's a volatile market.
And also some governments say maybe we do this. You know what I mean?
Yeah, there's also, I mean, that is one part about where the governments want to go.
Yeah.
But also there's a huge regulatory concern there that has nothing to do with research.
That's right.
I'm Austrian, I can tell it for Austrian perspective. If I drive from Vorarlberg, which is the most western part, to home, I pass through several districts, municipalities, different regulations. It changes how I transport hydrogen, although it changed nothing about the vehicle. So that there's a mess in just one country. Look at Europe as a whole, look at the world as a whole. We have a lot to do on the regulatory side as well.
Thank you.
Also die letzte Frage wird phasenlich genommen. Okay, so let me switch to English again. So you have shown in your presentation the chemical side of this problem, right? But there is also a physical side. And you didn't mention at all about the flow, phase changes, the creation of nanobubbles, flow through porous media, and so on and so on. Yeah, there are many different things here that are interesting for fluid dynamics.
Yes.
Dynamicists. Yeah, and how do you chemists deal with that? Do you have a group of people who are doing this for you? Do you have some cooperation with universities that are somehow try to resolve for you these flow problems? Because this is a quite big topic here, right?
Yeah. I touched upon it very briefly, that this research is very, very interdisciplinary. Yeah. And there's no right or wrong background essentially for it. Because there's physics is as much of importance as chemistry, is as important as mechanical engineering.
Let's go to the point.
Yes.
When you do an analysis of your cell, let's say, are you interested only in the amount of the hydrogen produced overall, integrally in the whole device, or do you analyze also what happens on a very small scale? What processes are occurring on the surface of the membrane? You understand what I mean? Yeah? How ions are distributed in the concentration of ions, right? And so on. How they are changing in time, because this will be different in the beginning of the production, and then when the equilibrium comes, and then.
to still touch a bit upon your first question, yes, we collaborate, especially in design aspects, especially in terms of to see, because you have to base it basically on CFD simulations to have the right, you have flow fields, you have of course layers to optimize these. The only way that we have is simulations, of course, and there naturally we collaborate. And where there's also, in relation to your second question, a huge gap, actually. So especially when you look into the details,
Yes.
you are getting very heterogeneous also over a cell layer. So there's a limitation with how much you can actually resolve in a reasonable time frame with simulations.
Okay.
So there also we collaborate, there also is work on this, but there's still quite a lot of lack there in order to really resolve that well over the full surface of a cell. Because when you look at nanometers, but your cell is 100 square centimeters, it's two worlds. Exactly. So it's different aspects, yes, of course, but this is very much something that is still research, where there's not really a good solution for it.
Thank you very much.
Sorry, one more question from my side. You focus mostly on thermal electrolyzers and fuel cells, right? But there are, let's say, 3 more technologies.
Yes, at least, yeah.
And obviously alkaline is the most mature one,
Yes.
the cheapest one, the most, the biggest, and the one that can theoretically produce most hydrogen. Do you think if alkaline electrolyzers advance, too much, or they become sort of the dominant one, and they will be able to be coupled with renewables pretty much the same way as thermal electrolyzers will be? The rest of the technologies will not be needed. Let's say thermal electrolyzers won't be needed because they're too expensive, not super scalable, not.
Yeah. Possible.
So
Possible,
basically,
but
in principle,
yeah.
in case alkaline electrolyzers become the dominant one, they become coupled, kind of suitable for being coupled with renewables. There won't be a need for any other technologies.
I mean, this is something really like I would love to have a crystal ball or to foresee the future. Hard to say. We just talked before that there is research that says alkaline can be coupled with renewables, which is a huge issue of that technology. But there's more to that. Not so much in the coupling, but in the feed. Alkaline electrolysis, I'm not sure, I would guess you need the electrolyte being pumped even for AEM. You use still potassium hydroxide solution, you still actively pump an electrolyte. Makes it bulky, makes it big, makes it also susceptible to, if you get CO2 in it, you have a problem. If you actively need to pump something, you can get all kinds of contaminations in. Alkaline has more trouble than just the direct coupling with renewable energy. So if you need something where you don't have a lot of space to produce your hydrogen, there could still very much be a viable niche for PEM if alkaline solves the direct coupling issue. So I don't think that any of the technologies would be completely off the table, but of course in the end, this is where I would love to have the crystal ball to foresee the future, because in the end, availability, and if I go to a manufacturer and I say I want an electrolyzer, what they sell me is going to also define of what I take, because it's, if one I can have and the other one I should do a development project of 4 or 5 years and then I can have it, there's no choice, right? So this is a tricky one. This is something where it will depend a lot on things that have actually not so much to do with research, but also more the financing and the scale up and where the money is. No more questions?
I'd like to touch upon storage of hydrogen. I heard that it poses some problems, and it's for example, there are 2 car manufacturers nowadays who mass produce cars which use hydrogen instead of petrol. And they need bulky, heavy containers. And what are the
car manufacturers is to do compressed hydrogen, 700 bars in composite carbon fiber composite tanks. These are the ones that you're referring to. Thick layers, yes, bulky, but at the same time, hydrogen has, it's doable. You can still reach quite reasonable distances with these tanks in those cars. Alternatives, difficult, because actually none of these alternatives have that high energy densities or storage densities. So altogether, we're always talking about somewhere like 4, maybe 6% of hydrogen compared to the tank. It's tricky. Anyhow, there's of course metal hydrides, there's liquid hydrogen. These all have very unique, again, challenges in it. Whether you have boil off or whether you have to deal also with the aging of your material that you store in.
So you can liquefy hydrogen.
Yes, you can cool it down.
Cool down and
exactly.
Could it be used the way ship tankers are used today to be transported, let's say, from the place where it's produced in North Africa to areas where there's the consumption takes place?
Yeah, I mean, especially for this type of like long distances of transport of hydrogen, it's something that's being looked into more for Australia connecting to Japan, actually. They are doing liquefied hydrogen tanks on ships, on maritime, but there's also a lot of interest to use something else, of course. So there's ammonia being discussed, there's all kinds of alternatives being discussed. The issue you have with liquefied hydrogen is that you have to actively cool. That takes a lot of energy. You have boil off. If you can use your hydrogen on board to supply your energy on board of the ship, you gain something. But it's complex systems you need behind this.
Can be translated and changed to ammonia, right?
Yeah, for example. Yeah. But then, of course, you have losses with that. You need to. We've talked about efficiencies before. You first need to produce your hydrogen, convert it into ammonia. You have losses. Convert it back maybe to hydrogen or use the ammonia, depending on where you want to go. But still, you lose your efficiencies.
Still, it gives some opportunity for areas which has a lot of sun, but
exactly.
are poor on other resources like Africa.
Yeah, exactly. Yes.
May I ask a comment on this question, because it's basically what our research group worked on, specifically on the transportation part. So I think most of the companies look at the 4 options right now: liquefied hydrogen, liquefied ammonia, the so-called liquid organic hydrogen carriers. Methanol is not the option if you're thinking about decarbonization as a whole in the long-term perspective, because it contains carbon in small molecules. So the 3 remaining options: liquefied hydrogen requires cryogenic temperatures, minus 253 degrees, which is very close to the absolute zero. It also means that you will be using roughly between 35 to 40% of the energy contained in hydrogen just to liquefy. Well, gas loss is super huge. There's only one vessel specifically designed for liquefied hydrogen transportation, so shipping hydrogen from long distances. Only one so far. There are more to be designed in the future, so most people, most companies at least, I'm not a proponent of any of the technologies, but most of the companies so far are leaning towards ammonia, because ammonia itself is much more compact as a molecule. So you can deliver more hydrogen using ammonia than liquefying hydrogen itself per unit of volume. But obviously with ammonia there will be a different challenge, because you will have to crack it to extract that hydrogen if you need to use it directly after you deliver the ammonia. So sorry for stealing this part of the question.
Yeah, thank you for the insight.
What if energy density of the hydrogen it's 3 times lower than fossil fuels? Is there any? Do you believe that there will be any progress in this?
That's the government believe in this.
I don't think it will change physics.
Yes, I don't do it.
I mean, hydrogen has a high energy density if we look at weight, has a low energy density if we look at volume, no matter how much we compress it, and we will not change physics. No.
Simply bigger tanks.
Yeah. Of course, as pressurize, cool down, increase the density of the hydrogen altogether. Sure, that's a goal, but physics will not change.
Also Your team, international team, I say 2 times, is also the Polish people or not?
Not yet.
I know. Very intelligent answer, I know. Because everybody just moving to China and Japan. Yeah, it's about the Polish science point of view. It's nothing to do here. Thank you for your intelligent answer. Because sometimes we need the help, but it's not a good specialist of this point in Poland.
Yeah.
Of the science.
But I do have an international team,
Yeah, I saw.
and I am very happy of having an international team because it's great to have different points of view coming in. It's really enriching, and if there's any, I'm always happy to.
It was a very polite question, no question.
No. Thank you. I took it as that.
We don't see in Poland this problem of innovation. You know, this problem. It's about the science and politics, and the thinking about the global hydrogen. The point of the money for Poland, for example, or European Union.
Yeah.
That's right. This is a good answer. Thank you very much.
Thank you.
Yeah. Another question comes to mind. I'm not a physicist, so my question may be naive. I heard that helium is so volatile, so light that it escapes from interstates, and in some time there will be no helium left on Earth. But what about oxygen? What if it escapes where there's a hydrogen equivalent of a ship catastrophe at sea, and you have a broken container and it goes in, where does it go?
I mean, there's not a clear answer to that actually. There's some hypothesis of what happens. It might react in the atmosphere. I think there's not actually a clear answer to that. It's part of research, but at the same time, there's also a lot of need to put things into perspective. If we look at the amounts of methane escaping right now, doing all kinds of things to our atmosphere, I think we're pretty far away from having to worry about hydrogen.
Well, smart question. Do you think so in Europe in the next 10 years will be most valuable of the cars electric or hydrogen?
In cars, I think battery cars are right now
Battery cars.
here. Yeah, I think there's a reason. I think there are applications where hydrogen cars would make sense. Fleets, for example, could make more sense for taxis, for example. I think it could make a lot of sense to go for hydrogen. For private passenger cars, I think battery cars are here, and I think that the benefits that a hydrogen car would have is they're not that big anymore. So I think
But
for
production
cars,
is still of the Toyota or something, The Toyota product,
Exactly, yeah. No, but as I said, I think I can see a use, for example, in fleets. If you have a taxi company operating some Mirai, I can see that.
the Erdgas in Austria.
Sorry?
In Austria, you use the Erdgas. There's some different gas. Gas, not petrol.
Yeah, sorry. Yes,
the
yes.
white cups.
Yes,
We talk about Germany and Austria.
Yes, okay.
Now you see the petrol.
There I could see the use of it. There I think it would make sense because there you need quicker refueling times.
Right.
You don't want to.
600 kilometers.
Exactly. You can just fuel it almost as quick as a diesel car, which makes for taxis, for example, a big difference. Right. You can also organize infrastructure easier, or also with any kind of logistics. I can see the use for a private person. I don't see the benefit right now of a hydrogen car as much as battery makes more sense.
That's right.
That's my view, my personal view.
Yeah, it's your point.
Yeah.
And there's some discounts in Austria for when you are a company and you use the hydrogen, you have some discounts for a tax or something like that. Bundesamt or the under.
There's support, I would say.
In Poland, no.
Should be.
Perfect.
Thank you very much. Thank you.